Look at a map of major shipping routes across the Pacific Ocean. You'll notice something strange. Ships traveling between Asia and North America follow paths that curve far to the north, passing near the Aleutian Islands and sometimes crossing waters above the 40th parallel. But if you look at where the deepest parts of the ocean are, places like the Mariana Trench, which plunges nearly 11 kilometers below the surface, you'll see they're much further south, in more direct routes between continents. So here's the question. Why don't ships just sail straight across the deepest parts of the ocean? Is it dangerous? Do ships avoid deep water for safety reasons? Or is there something else going on that has nothing to do with depth at all? Today, we're breaking down why ships don't sail through the deepest parts of the ocean, why ocean depth is almost irrelevant to commercial shipping, and what actually determines the routes ships take across thousands of miles of open water. And I promise, after this video, you'll understand that navigation is about geometry and economics, not depth. Let's start by clearing up the most common misconception. Ships do not avoid deep water because it's dangerous. Depth in itself presents no operational risk to surface vessels. Whether a ship is floating over water that's 50 meters deep or 10,000 meters deep makes no difference to hull stress, propulsion efficiency, or navigation. A floating ship displaces water at the surface. The buoyant force comes from the water immediately surrounding the hull, not from water thousands of meters below. As far as the ship is concerned, the ocean could be infinitely deep, and it would behave exactly the same way. Depth only matters for submarines, underwater cables, and deep-sea operations. For surface ships, it's irrelevant. So if depth doesn't matter, why do shipping routes avoid the deepest trenches? The answer is simple. Those routes aren't actually shorter. And in commercial shipping, distance equals time, and time equals fuel, and fuel equals cost. Every nautical mile a ship travels burns fuel. Every hour at sea costs money. Shipping companies optimize routes to minimize distance, not to avoid deep water. And the shortest path between 2 points on a sphere is not a straight line on a flat map. It's a curve called a great circle route. Here's where geography and mathematics intersect. The Earth is a sphere. When you look at a standard Mercator projection map, which is what most people are familiar with, straight lines appear to be the shortest distance between 2 points. But that's an illusion created by the way the map projects a spherical surface onto a flat plane. In reality, the shortest path between 2 points on a sphere is an arc that follows the curvature of the Earth. This is called a great circle, and if you plot a great circle route on a Mercator map, it looks curved, but on the actual globe, it's the most direct path. Let's use a concrete example, a ship traveling from Shanghai to Los Angeles. On a Mercator map, a straight line between these two cities would pass through the Central Pacific, crossing near the Mariana Trench. But if you measure that path on a globe, it's actually longer than a route that curves north through the North Pacific. The Great Circle route between Shanghai and Los Angeles passes near the Aleutian Islands, far above the Mariana Trench. This northern route looks longer on a flat map, but it's shorter on the globe. And shorter means less fuel, lower operating cost, and faster delivery times. The difference isn't trivial. A Great Circle route can save hundreds of nautical miles compared to a rum line, a path that maintains constant compass bearing. Over a trans-Pacific voyage, that could mean 500 to 1,000 nautical miles saved. At a cruising speed of 20 knots, that's 25 to 50 hours of travel time eliminated. For a ship burning 200 tons of fuel per day, that's 200 to 400 tons of fuel saved. At current bunker fuel prices, that's hundreds of thousands of dollars. Multiply that across hundreds of voyages per year, and the savings become massive. Now, Great Circle navigation isn't always followed exactly. Real-world routes deviate from the theoretical shortest path for several reasons. Weather is a major factor. The North Pacific in winter can be extremely rough, with massive swells and storm systems. Ships may deviate south to avoid the worst weather, even if it adds distance. This is called weather routing, and it's a calculated trade-off. Taking a slightly longer route through calmer seas can reduce fuel consumption by allowing the ship to maintain optimal speed, whereas fighting through heavy weather increases drag and forces the ship to slow down or expend more power. Currents also matter. Ocean currents like the Kuroshio Current in the Western Pacific or the California Current along the North American coast can add or subtract several knots from a ship's effective speed over ground. A ship traveling with a favorable current can save significant time and fuel, even if the route is slightly longer. Conversely, fighting against a strong adverse current can negate the advantage of a shorter route. Navigators use current data to optimize paths dynamically, sometimes adjusting course mid-voyage based on updated oceanographic information. There are also regulatory and practical constraints. Ships follow designated shipping lanes in congested areas to reduce collision risk. Traffic separation schemes near major ports, straits, and coastal regions force ships into specific corridors. Piracy is another consideration. Certain regions, like the Gulf of Aden or waters near the Horn of Africa, require ships to follow routes protected by naval patrols or to increase speed and take evasive measures. These deviations have nothing to do with ocean depth and everything to do with security and traffic management. Now let's address the Mariana Trench specifically. The Mariana Trench is the deepest point in the world's oceans, reaching nearly 11,000 meters at Challenger Deep. It's located in the Western Pacific, east of the Mariana Islands. So why don't trans-Pacific ships pass over it? Because the Great Circle routes between major port pairs simply don't cross that region. A ship traveling from Japan to the U.S. West Coast follows a northerly arc. A ship traveling from Southeast Asia to Panama follows a more southerly route. The Mariana Trench sits between these corridors. There's no major trade route that requires passing directly over it. It's not avoided, it's just not on the way. There's also a deeper point here about how trade routes form. Shipping lanes aren't arbitrary. They connect economic centers. Ports in China, Japan, South Korea, and Southeast Asia ship goods to ports in North America, Europe, and other regions. The routes are determined by where the cargo originates and where it's going, not by random points on the ocean. The deepest parts of the ocean often lie in remote regions far from major trade corridors. They're not avoided intentionally. They're just not along economically relevant paths. But let's explore a hypothetical. What if a ship did sail over the Mariana Trench? Would anything happen? No, absolutely nothing. The ship would float normally. Navigation systems would work. The engines would operate as usual. The only difference would be that if you dropped a weight overboard, it would take a very long time to reach the bottom. Depth does not affect surface navigation. It doesn't create unusual currents at the surface. It doesn't generate dangerous conditions. The Mariana Trench is only significant if you're diving into it, not sailing over it. There is one scenario where depth becomes relevant for surface ships. Shallow water. When a ship operates in water depths less than about 2 times its draft, hydrodynamic effects change. The ship experiences increased drag because water squeezed between the hull and the seabed accelerates, creating pressure differences. This is called shallow water effect. Ships slow down in shallow channels and coastal areas, not because of risk, but because drag increases and fuel efficiency decreases. This is the opposite of the deep ocean. In deep water, there is no interaction between the hull and the seabed. Drag is determined entirely by the ship's speed and hull form. Another misconception worth addressing: some people assume that ships avoid deep trenches because the seafloor is unstable or prone to earthquakes. While it's true that deep trenches are subduction zones where tectonic plates collide, this doesn't create surface hazards for ships. Earthquakes at subduction zones occur kilometers below the seafloor. The energy released can generate tsunamis, but tsunamis are only dangerous near coastlines where they amplify. In the open ocean, a tsunami is a barely noticeable swell. Ships can pass over a tsunami without even knowing it. The wave height is less than a meter, but the wavelength is hundreds of kilometers. It's only when the wave enters shallow coastal water that it slows down, compresses, and rises to devastating heights. So tectonic activity near deep trenches is not a reason to avoid them. Let's also talk about undersea features that ships do care about. Seamounts, underwater mountains that rise from the seafloor but don't reach the surface, can be hazardous if they're in shallow enough water. An uncharted seamount with a peak 50 meters below the surface can damage or sink a ship with a deep draft. This is why hydrographic surveys are critical. Nautical charts mark known seamounts, reefs, and shallow features. Navigators avoid these areas carefully. But seamounts in deep water, thousands of meters below the surface, pose no risk to surface ships. There's one final factor: fuel optimization software. Modern ships use computer systems that calculate the most efficient route based on distance, weather, currents, port schedules, and fuel prices. These systems process real-time data and can adjust routes dynamically during the voyage. The software doesn't include depth as a variable because it's irrelevant. It focuses on factors that affect fuel consumption and transit time. The result is a route that maximizes efficiency, and that route is almost always a variation of the Great Circle Path, modified for weather and traffic. So, to answer the original question, ships don't sail through the deepest parts of the ocean because those areas aren't along the shortest routes between major ports. It has nothing to do with danger, difficulty, or operational constraints. It's pure geometry. The Earth is a sphere. The shortest path between 2 points is a great circle arc, and those arcs, combined with economic considerations like weather, currents, and port locations, determine where ships actually go. The deepest trenches happen to lie outside those paths. They're not avoided. They're just not relevant. This is a perfect example of how intuition misleads us. When you look at a flat map, it seems like ships should cross the Central Pacific in a straight line. But the Earth isn't flat. Navigation is three-dimensional, and the shortest path on a sphere is counterintuitive when projected onto a flat surface. Understanding this changes how you think about global geography, trade, and transportation. It's not about avoiding obstacles. It's about finding the optimal path through a curved space. The next time you see a shipping route that curves across a map in a way that seems inefficient, remember that maps distort reality. The route that looks curved is actually the straightest possible path on the globe. And the deepest parts of the ocean, dramatic as they are, don't matter to ships floating on the surface. Depth is irrelevant. Distance is everything. And distance on a sphere follows rules that flat maps can't accurately represent. If you've ever wondered how ships actually navigate and plot these routes in real time, I've already covered that in another video.